Okay, a brief recap of what we have learned in the first part of our lessons. We have finished the first part. That is the one in which the problem is directly quantified a parameter, a quantity. So the statistics of replicate measurement. And we have learned that starting from a statistical sample, that is a series of measurements of our parameter x, we can predict the confidence interval of the mean by writing x average plus minus t student depending on the level of risk that we accept, significance, the degrees of freedom, the difference between the number of measurements and the number of parameters, multiplied the standard deviation of the sample divided by the square root of n, and we can also rewrite in an equivalent way because Sx over square root of n is the standard deviation of the mean. Then we learned some significance tests, the two basic ones that are t-tests for assessing trueness. So we suppose that we know the reference value that we named xk. K means known or expected. And we defined the t-test for assessing trueness. And the f-test The F-test is concerning the case in which we compare our confidence interval with another. So in this case, simple, we learned the t-test. And what we learned is that the parameter t, in general, is equal of a fraction, the fraction. In the numerator, we have an absolute value. In the denominator, we have a standard deviation. The absolute value is the difference between the experimental value and the known value. Divided by the standard deviation of the experimental parameter. This is generalized. Why do I need this generalization? Because in the second chapter of our studies, we will learn how to compare other kinds of results by using t-test. In this case, experimental is the average measured from our statistical sample. The known is xk. And S experimental is the standard deviation of the mean in this case. Okay? In the case of the simple t-test. Then we learned, still in the chapter replicate measurements, how to compare two confidence intervals. It means that we have two series of numbers. One operator measures the standard deviation, the average and the standard deviation of a sample of measurement of x. So the first operator obtains x average 1, the variance 1, and the number of degrees of freedom 1, And we wanted to compare this series of numbers with the reference series of numbers, that is the same measurement performed in a very reliable way, so reference values. And they are x average 2, s squared 2, and need 2. And we discussed that in order to compare the two average values, we need a t-test. In order to compare the variances, we need an f-test. And the t is expressed in general in this way. So tk is equal to x average 1 minus x average 2. Sorry, it is not a bracket but absolute value. Divided by square root of S1 squared divided by N1 plus S2 squared divided by N2. When the f-test decides that the two variances are not significantly different, this formula can be simplified, but it is not important now. The f-test is obtained by calculating an fk, and in analytical chemistry we decided that we calculate the ratio between the two variances, but we put at the numerator always the higher number of the two. So we have s squared higher divided by s squared lower. In any case, in a significance test, that is a test comparing the quantities, we have that the decision criterion is obtained by comparing the tk or fk with the corresponding tabulated. And the tabulated is the best value that corresponds to alpha, our level of risk. So, to decide to take a decision in a subjective way, we can compare tk with the t. I think I have to substitute my pen, sorry. I will try until it expires. If tk is less than t tabulated, alpha n, we have used tabulated, but it's the same. We decide no significant difference. If fk is less than f tabulated, we decide no significant difference. This is subjective. When we want an objective result, we consider the p-value for t, which goes from 0 to 1. P-value for t-test from 0 to 1. And the p-value of f-test goes from 0 to 0.5. The p-value in general is a degree of similarity between the measured quantity and the reference one. So when we have high similarity, we have the highest value. When the two compared quantities are totally different, we have p-value equal to 0. We can also compare in a subjective way the p-value with alpha. So in general, if p-value exceeds alpha, we conclude no significant difference at the level of difference that we have, the level of significance that we have chosen. Okay? This is all we have learned in the first part. Now we move to the second chapter. The name is calibration. I think I have to substitute the point of this pen. Just a minute. Okay. So calibration. Instead of giving a definition of this procedure, which is crucial in analytical chemistry, let us start from an example. So suppose that you have a painting, so some picture that you want to analyze, and or you have some artwork and you want to understand whether collagen is present. So what would you do? You would take a small aliquot of the artifact, small sample, and you weigh it so you know the mass. Then you put this small quantity of material in a solvent and you obtain a solution. So by measuring the concentration of the analyte of interest in that solution, you can obtain the original percent of analyte in the original mass. Okay? This is an example. Suppose that in this sample you are looking for hydroxyproline. It is a marker for collagen. Did you learn that? Mm-hmm. Okay? Mm-hmm. And a possible technique is HPLC. Did you study liquid chromatography? Mm-hmm. Okay? So you take a small volume, that's small microliters of that solution. This is the unknown solution. And you inject in the instrument. And what you obtain in this example, so example, liquid chromatography, to obtain hydroxyproline. Let us call it analyte. This is the analyte. Hydroxyproline is in that solution. It is together with a lot of chemical species, and the rest of the analyte, with respect to the analyte, is called the matrix. So the sample, the chemical sample, is analyte plus matrix. Okay? And now we inject, and what we obtain is such a plot. This is the time with respect to the instant of injection. It is 0. At the time I inject it. And you have a quantity in the vertical axis. It could be absorbance. In general, we say a number that quantifies something, and we call it the signal. It is uppercase signal. Analytical signal. Maybe, for example, absorbance. you see something like that. A lot of things inside. Which is, in this picture, the position corresponding to my analyte. I take pure hydroxychloride, I solubilize it, I inject, I will see only one peak. Suppose that we see this peak. Then we inject again hydroxychloride, but more concentrated, and we see that that peak increases the height and area. This area is the numerical quantity allowing me to calculate the concentration. I want the concentration of my analyte in the injected sample. Okay? Is it good for you? And the very useful, there is a very useful theorem which has been demonstrated by experimental studies. The area is directly proportional to the concentration. So I have this theorem. Area is equal to a constant, here K is a constant, multiplied the concentration. This is the law, the chemical physical law linking area with concentration. So area, called signal or response, we can call it response or signal equivalent and the quantity C is our independent variable. We would like to measure X. We cannot measure it directly, so we measure Y, the signal, and calculate X from Y. So we need to find the function, to define the function linking the response to the independent variable. Okay? The statistical procedure allowing us to find the calibration function, this is called calibration. Sorry, it was a tautology, I will repeat. The statistical method allowing us to obtain that function f is called calibration. So, performing calibration of an analytical method means to find the function linking the wanted quantity x to another quantity y, that is the signal to be directly measured. This is calibration. Calibration is finding this equation. Of course, in the case of liquid chromatography, the function is area equal K multiplied C. This is the function. So, the equation useful calibration is this one. Calibration equation. For LC, liquid chromatography. Okay, this one.
So calibrate in the case of liquid chromatography means finding that equation.
Yes. And finding this equation means simply to estimate K. That's what we need. Because if we obtain that constant K, we can trivially divide the area by K and obtain the concentration. Yeah? Cool? Okay? That's okay? Unfortunately, K cannot be calculated by a formula. And this is because K depends on all the possible experimental conditions in our experiment. So, the nature of the carrier, mobile phase, liquid, flowing, it can be water, it could be another solvent, a mixture, it could be a lot of things. Depends on temperature, depends on the nature of the solid that is filling the column. Okay? Stationary phase, we have studied this term. There are very small particles filling the column, and the carrier flows through these particles, and these particles allow separation. Okay? So K depends on everything. But we ask help to the statistics. We can estimate K by a statistical procedure. The statistical procedure allows us to find an equation that is the best estimation of the load. So, and now I will change these terms. I can, it is better, substitute, please, equation is with function, it's more generical. And then we move to the procedure of finding an estimation of the true equation. Okay? So the true equation, the law, is area equal a constant multiplied concentration. We will,
But we said that this function.
This is a function, yes. Okay. Let's use, I use different terms because I wanted to make a distinction between what is theoretical, the function, what is experimental, the equation that we find. So the function, the true function is this. I will estimate it by an equation. I write and then I will discuss. Area equal to a constant term plus another constant multiplied concentration. This is the model, statistical model that is the best estimation of the function. You could say, you could ask me, but why did you put this constant term here? Because in the original function, there is not a constant term. The original function can be written like this: 0, 0 plus k multiplied c. So theoretically, when c is 0, the area should be 0, okay? But when we try to obtain the experimental model, there are errors. So it may happen that the quantity that we obtain when c is 0 is small, very small, but not identical to 0. Maybe it can be more clear if I draw the plot of the two equations, the function and the model. So in theory, we have that if we put c on the horizontal axis and area in the vertical one, the plot should be this: a straight line passing through the origin of the axis. Okay? It should be like that. But how will I obtain this? How will I obtain an evaluation, an estimation of the red straight line? I will do like that. Okay, don't cancel your, delete your draw. I will redo it more small because I want to make direct comparison in my slide. So here you have the true function, and on the right I will draw the model. The procedure to obtain a green straight line that is a good estimation of the red one is to prepare a series of solutions containing only hydroxyproline as an analyte in a solvent. So I prepare many. They are called standard samples, that are solutions where the analyte has a known concentration decided by me. So, for instance, I can prepare 5 samples where the concentration of the analyte is decided by me. These are standard samples. Or standard solutions. Then I take the first one, in which the analyte has concentration C1. I inject in the LC instrument. I obtain one peak, and this peak has an area that I call A1. So I have here A1, and here I have a point. Okay? Is it clear the meaning of the green dot? And then I do the same for the 5 standard solutions. I would expect all the points stay on a straight line, but there are errors. And the points will have a linear trend but where they will be not exactly on a straight line. I will find something like this. So 5 points with a linear trend, but not exactly staying on a unique straight line. Is it clear for you?
I have just a question. Now, we used 5 standard samples with increasing quantity of analytes, whose matrix is similar to the one of our sample.
We will discuss later of the matrix. Okay. As for now, the matrix is a very simple solvent, and we suppose that the matrix and the solvent are equivalent.
Okay.
Then tomorrow we will discuss in general about the matrix.
But since they are standard, these errors, for which they are not in a straight line, are due to the instrument.
Are due to the instrument. Okay. And I add another important information. We suppose that the error that we make on the standards in preparing the standard samples is negligible with respect to the error on the area. In fact, when you perform liquid chromatography, even if you replicate the same injection of the same standard, you will see values of area that are very dispersed, not so similar. We say that the reproducibility is low. So we have a big error on the area and a negligible error on the concentration of the standard samples. Okay? But even if there is not a single straight line that is passing through all the 5 experimental points, yes?
But we consider also the errors due to the instrument negligible.
You mean to the signal?
Yes.
It is a mixture. The signal, that is the area, is a mixture of the absorbance of the detector and other variations. Okay? So when you inject, say that the second peak is the analyte, you take a standard sample, you inject many times, and the areas are very dispersed. And this is depending on the instrument, yes. The random variations of experimental conditions during the analysis, for instance, temperature.
But we consider, because we said that we don't have a straight line because we have errors that are due to the preparation in the standards and also in the instrument.
Yes, but the error relevant to preparation in the standard is negligible. Okay. Only error in the area.
Yes, instead the one of the instrument are negligible with respect to the area.
But the instrument is giving to you. You mean this signal, the S in the chromatogram?
No, well, we said that when we prepare the standard and we make calibration is not. We prepare the standard and we measure the signal, and we obtain a point that are linear, so they have a linear distribution, but not perfectly on a straight line. And we said because there are errors, and Martina said these errors are due to the instrument.
Yes, they are due to the instrument and to the experimental conditions. For instance, temperature can change slightly during your experiment. So since K, the constant depends on everything, also the temperature, you will see that the area could change from one injection to the other of the same sample. So all the uncertainty of our experiment is in the area, and maybe the detector has a low contribution, but there are other parameters contributing to the area. So it is a variability that is intrinsic in the experiment. The variability of the area is characteristic of the experiment, and it depends on the random variations of all the parameters that are influencing K. In fact, what is particularly subjected to variations is K. K is the main cause of variations. And also, of course, you can have some uncertainty on the signal. That is this quantity, the signal. Okay?
Yes, so this.
I think you don't understand you.
No, I understood. So these are not negligible.
No,
Okay.
they are not.
Okay.
And moreover, there is also another important fact that the operator can be more or less accurate in doing experimental actions. So you have fluctuations, variations of these points, but they keep a good linear trend. Okay? So it is enough for us, it is enough to find a straight line that goes close to the points. Okay? Now our statistical problem is to find that straight line that gets as close as possible to the experimental points.
Okay.
And this straight line is the model. And you see this, this small segment here, this small segment corresponds to which parameter in this equation? A, lowercase. And this A is called intercept. This is the intercept. Okay? So it will be enough for us to demonstrate that this intercept is very close to zero, very small. And we will demonstrate it through a t-test. Okay? The expected value for the intercept is 0. Okay? So we will discuss how to demonstrate that the intercept is not significantly different with respect to 0. Okay? But we need to put that constant and evaluate it. And yes?
I'm sorry, I didn't get the connection between this graph and the other one with the areas. Like this one is absorbance versus concentration.
Yes, and also the other one. This is still area. Our signal is the area.
Area versus concentration.
Yes,
Okay.
A in this symbol is area.
Okay.
I wrote simply A for simplicity.
Okay.
the area of the chromatographic peak corresponding to my analyte. This is the signal.
Okay, yes.
Okay.
And this is sufficient?
What?
No. Is this sufficient to demonstrate that they are not so predictable?
Yeah. If I demonstrate that my model has a not significant intercept, it is good model. Yes.
Older model. Older
Yeah.
model. Okay.
Since we have a complicated matrix, wouldn't it be better to use the method of standard addition?
We will discuss this method tomorrow, standard addition method, because in general, this method that I am describing, that is called the external standard method, is convenient. Because as I will demonstrate tomorrow, the other alternative method is very busy, it requires a lot of experimental work and it is less precise. So we start studying the external standard method and then tomorrow generalize with the standard addition method. Okay.
I think like the 1/3 to the first 1/3 of this calibration line, the error increases.
Yes, it might happen. It might happen, but we have formulas that allow us to calculate the error. But we are going ahead too much, so we need step by step for the students that did not learn these concepts. Okay, so this is the external standard method. That means that the solvent where we dissolve the analyte is a convenient solvent, not necessarily identical to the matrix. For instance, if I want to quantify copper in this water is a very simple matrix. It is very similar to the water in the lab. So in this case, external standard will work. If I take a very complex matrix, I need standard addition. But I can study the effect of the matrix, and tomorrow we will study the matrix effect. As for now, let us suppose that the solvent is equivalent to the original matrix. Okay, let us suppose that. Okay, and we obtain this model where the constant, the intercept, is estimating 0 in a certain sense, so it should be close to 0. And the other parameter b, called slope, is our best estimation of k. Okay, so the model estimates the true function. And finally, what will I do? I will measure the area for my unknown sample. Okay, I call the area of the unknown A0. So A0 is area for the unknown. It is the unknown sample. And I find that point of the straight line of the model that corresponds to A0 and go down and read the corresponding concentration that I call C0. This procedure is called interpolation of the unknown signal on the model. Okay?
Can you repeat the definition of interpolation?
Interpolation is finding the value of concentration that corresponds to the area of the unknown sample. And this is right on the model. Is it okay for you?
I measured the area of the unknown sample.
And this area is A0.
A0, okay.
I look for the point of the model that has this area as the ordinate and find the abscissa of this point interpolated on the model.
So it's finding the concentration that corresponds to the concentration of the analyte in our sample in this plot.
Yeah.
There is a calibration curve.
This is yes, the model is the calibration model, and this procedure of reading the unknown is called interpolation on the model. Would you like a little break, or will we go on 10 minutes? Because this, it seems simple, but it is very complex statistics. Because we need, I can anticipate an issue. How should we choose C1, C2, C5? How? Because it is we decide the value to be given to C1. 1 ppb, 1 ppm, 10 ppm, 100, how much? Okay? So we need to study some basic statistics to decide the concentration to be given to the standard samples. This is projecting the experiment, projecting the standard samples. And in order to do that, we need statistics. So I will show you. Okay, 10 minutes break. Okay. Okay. What have we discussed up to now? We want to find the model that is the best estimation of the true function. And at the beginning, for simplicity, we suppose that the matrix is not influencing the signal of the analyte. I mean, the signal of the analyte is the area, and we suppose that the value of this area is independent of the matrix nature. That is equivalent to say that we suppose that if we dissolve the analyte in a convenient solvent, this solvent is equivalent to the original matrix. This is an hypothesis for simplicity, and tomorrow we will generalize and study the matrix again. Okay? And we said that in order to calculate the model equation, we should prepare some standard samples using a convenient solvent. This is external standard method. We obtain all the green points in the green plot, and we want to calculate the straight line that is fitting these points. This calculation is called regression, statistical regression. So making a regression, allows us to start from some values CI area I, and from this calculate intercept and slope. Better to write the names. Calculate intercept and slope.
I'm sorry, Professor. Regression is calculating intercept and slope.
Yes, starting from the n points, Ci area I. Yes, because the subscript I goes from 1 to n. In the example before it was n equal to 5. Okay, so you have 5 points, C1 area 1, C2 area 2, C5 area 5. So you have these experimental values and you want to calculate the intercept and the slope. Starting from those numbers. Okay, this is regression. And doing this, calculating the equation, is called, in statistics, creating the model. So, in the first part of our work, we prepare some standard samples and using the numerical values of the concentration and the areas of these standard samples, we create the model, that is, we obtain the equation area equal to intercept plus slope multiplied concentration.
So creating the model is equal to, say, calibrate.
Creating the model allows us to obtain calibration, because calibration is the procedure that allows us to find the relationship between the signal and the concentration. In this case, between area and concentration. So we calibrate the method by finding the model that is the best evaluation of the true function. This is calibration. Okay?
I'm sorry, I didn't get what creating the model is defined.
Creating the model is defining this, calculating intercept and slope.
In a statistical language.
Yeah.
Okay.
When a statistician tells to you, I want to create a linear model, means that he or she wants to calculate the intercept and the slope of the linear model. Of course, we suppose that the model is simply linear, like this one, because in multivariate analysis there are multivariate models. But here we are univariate model because there is one independent variable, the concentration, and one dependent variable, in this case it is the area. Okay? Okay, and how can we perform a regression? Now I will explain the statistical procedure of regression. Let us start from, now I will draw all in black and use color for indicating some particular quantities. So here I put concentration. Here I put the area. And now I'm going to draw the points corresponding to standard samples. So, for instance, one here, too much high, sorry. Make better. One here, and like that. And the model is this. This is the model. Which is the quantity that accounts for how close the points are to the straight line of the model, it is the distance. So I want that the distance between each point and the model be as low as possible. Okay? So I will draw this distance. Now I will use the green. I have a few colors, but green doesn't mean now experimental. It's simply a segment. For instance, for the fourth point, it is this. I calculate the distance vertically because I have supposed that the variability on concentration is negligible. So I calculate the distance between this experimental point and the model by making the difference, calculating the difference between these two values. Okay, in this case, let us focus on C4. So it is the concentration of the fourth standard. Okay, so let us discuss on this case. And in the ordinate corresponding to my experimental point, I have area number 4. Okay? We need now to calculate this value because we want the difference. Okay? And this value is indicated in statistics as A4 with the hat. Close. Nice. Okay, what is this A4 with the hat? It is the area that I read on the model when the concentration is equal to C4. Are we able to write this A4 with the hat as a function of intercept, slope, and concentration? Because the model, the equation of the model is area equals intercept plus slope multiplied concentration. So, if concentration is equal to C4, what is A4 with the hat? I will give the answer. A4, better figure something. A4 with the hat is equal to the intercept plus the slope multiplied C4. Is it true?
Yes.
So I call this value with the hat the value of area recalculated by the model. So A4 is what I have measured. The value of the area of the peak when the concentration is C4, the peak of the standard. Okay? And A4 with the hat is the corresponding value of area on the model. So we know that we want that this difference be slow, be low for all of the points. Okay? So we want all the green segments for all the points to be very small. And so I will generalize this writing it for the generic point with the subscript I. So, in general, A, the area, the area of the generic point I with the hat will be the area measured for the standard I is the intercept plus the slope multiplied the concentration of the standard I, and the concentration of the standard I corresponds to area of the standard I. So I want to check all the quantities area of the standard I minus the area with the hat of the standard I, and I want that the sum of all these quantities to be small, but when we consider the differences between two values, it is better to use the squared values. I mean, look at the green segments. If I take simply the quantity, in this case, if I take the quantity A4 with the hat minus A4, it can be positive. It is positive for the point number 4. So this is positive. It is better to discuss the inverse. So A4 minus A4 with the hat.
Yes,
it is positive. But A3 minus A3 with the hat is negative. So if I sum these segments as such, some of them will cancel the other. And I do not want that. I want all the absolute quantities to be summed. But we know in statistics that instead of absolute value of a difference, it is better to consider the square. Because the squares of these differences are linked to a variance, and variances are additive. I will show which variance I am talking about. So, I consider this sum, it is a sum of squares, and now I want to consider an average of this sum, but I do not divide by the number of points. The sum of squares should be divided by the degrees of freedom of this problem. The degrees of freedom of this problem. And now we want to decide how many degrees of freedom has the problem of regression, finding the model from the points. We can answer to this question by asking which is the minimum number of points that I need to find a straight line?
2.
It is 2 because in the equation we have 2 coefficients, the intercept and the slope. Okay? We have 2 parameters to calculate here, the intercept and the slope. Creating the model, obtaining its equation means to calculate intercept and slope. And to calculate them, the minimum number of standard is 2. So I could use only C1 and C5, the minimum and the maximum. But if I look for the straight line only with 2 standards, I cannot study the variability. I need to perform more than 2, to create more than 2 standards. So to exceed the minimum number of experiments required. So if the minimum is 2, but we have obtained 5 points, which is the number of degrees of freedom. I repeat the question. Okay. The minimum number of standard, that is of points in this plot, is 2. Because 2 is the number of parameters to be calculated, intercept and slope. But I plotted on this plot 5 points. That is more than 2. What's the difference?
It is n minus 2. So?
No? Yes, okay. Yes, n minus
3.
3. Okay? So, in the problem of creating a straight line model, the number of degrees of freedom is the number of measurements performed on the standard samples minus 2, that is the number of parameters that I am calculating, intercept and slope. Okay? Is it clear for you? Okay. This quantity that I have written here, if I put it under a square root, which kind of quantity is it?
Standard deviation.
It is a standard deviation. But I'm not comparing measured points with an average. I am comparing measured point with a recalculated value on the model. But it is a standard deviation. And the symbol is this. Standard deviation y over x, that is standard deviation of the regression of the response over the independent values. This is the generic symbol. Standard deviation of regression. And the square of the standard deviation is the variance of regression. Okay?
So it is the standard deviation of regression.
Of regression. And now we want to create the model, is calculate intercept and slope that make this standard deviation minimum. Okay, this is making regression is finding those values of intercept and slope which minimize the standard deviation of regression. Okay? Is it clear for you? Okay. Now, just a little bit mathematics for those who know something of mathematics, because this writing is an equation where the unknown values are the intercept and the slope. I will rewrite it to explicitate this, okay? So, I have square root of the sum of the squares of experimental values of the area minus values of the area recalculated on the model squared divided by n minus 2. And this means square root fraction, denominator is the same, numerator is the sum, square bracket, AI, so area for the ith standard, minus open round bracket, AI with the hat is intercept plus slope multiplied CI, close round, close square bracket, square. Do you agree that this is true? Is it clear for you? Okay? Now, suppose that C1 is 1 ppm, C2 is 2, and so on. So these writings are numbers. But also the areas for the standard samples are numbers. In this writing, the unknown parameters are the intercept and the slope. This is a function of the intercept and the slope. How can I minimize this quantity? That is, as we said, the standard deviation of regression. We make the derivative of this quantity, partial derivative of s y over x with respect to a, and put it equal to 0. And we find the value of the intercept minimizing it. And we write the partial derivative, first derivative of the standard deviation of regression with respect to the slope. We put it equal to 0. By doing this calculation, we obtain the value of intercept and the value of slope, minimizing the standard deviation of regression. So minimizing the average distance of the points, experimental points, with respect to the straight line.
Okay, what we have done, the derivative
of the function of the equation of for s y over x with respect to the two unknown parameters of this problem.
No. The derivative of our function is as
yes, the derivative of s y over x with respect to the intercept gives the best value for the intercept.
Sorry, by putting those ratios
conditions
equal to 0, we minimize what?
S y over x. This corresponds to minimizing the standard deviation of regression.
By doing the derivatives of the function with respect to the intercept and the slope,
Yeah.
but then we need to put this derivative equal to 0.
Yeah, because we are looking for the point of minimum, where the first derivative is null. And A, the intercept, results to be a combination of the values Ci and Ai. There is an equation, but I do not remember the equation, and it is not important to write it. We know that starting from our experimental values that are Ai, the experimental values that we have measured are the areas of the peaks for the standard samples and the concentrations. So the intercept and the slope will be calculated by equations where there are combinations of these values.
Can you repeat, please, what we have done?
Okay, we have written
in this last passage.
What exactly should I repeat?
We minimize what?
We minimize this quantity. This quantity is equal to this square root.
Because we obtain the minimum value for the intercept and the slope.
We obtain the value for the intercept and the slope, which make the standard deviation of the regression minimum.
Okay.
This is what we have done.
Okay.
Well, it is okay, but you know, when I calculate any possible statistical parameter, I do not give only one number, but also the uncertainty and the probability. So now I want to obtain the confidence intervals for the intercept and for the slope. I mean, I wanted to obtain these writings. The value of the intercept coming from regression, okay, plus, minus, an absolute error associated to the intercept with a certain probability or significance. This is what I want. Okay? And the same for the slope. I want this kind of result. The slope coming from regression obtained with this procedure, plus minus an absolute error with a certain probability or significance. I think that, according to my experience, it is easier to understand what I am saying if I describe this kind of ideal experiments. Suppose that we repeat an infinite time of executing this procedure. I make one experiment where I prepare 5 standards of known concentration, I measure the areas, and I obtain intercept and slope. And then I repeat this the same way, infinite times. Okay? Is it clear what I am imagining? Imagining. Do you understand? No? Okay, suppose that, okay, we go to this This plot is describing a procedure where I have prepared 5 flasks with known concentration. I have injected them into an LC system. I have measured the values of the areas, and I have performed the regression to obtain intercept and slope. Now I take an infinite number of operators who replicate exactly my experiment. And all of these operators will obtain a value for the intercept and a value for the slope. Now I can plot the results of all these infinite operators. For the intercept A, I will put on a horizontal axis all the possible results, the infinite values of intercept obtained by the infinite operators. Okay? And then I will put on the vertical axis the probability that the operators find the values of intercept on the horizontal axis. And of course I obtain a Gaussian distribution. And in this Gaussian distribution, we have as a point of maximum the best value of intercept. That is the number that comes from regression. So let us specify, this is the number that comes from regression, AR. AR is the intercept calculated by regression. Okay, that number. Okay? And it is in the maximum. It is the intercept coming from regression. The value of the intercept is characterized by, what is this?
Sorry, Professor, the one, it is the value calculated by regression but by which operator?
By this procedure. This is the regression.
Yes, but we said that different operators perform
Yeah,
the same procedure.
the infinite number of operators find infinite possible values of the intercept, and the maximum of the distribution is the one obtained mathematically by this way. So this procedure of minimizing the standard deviation of regression gives one value for the intercept that I have called AR. So AR is that number that comes from minimizing the standard deviation of regression.
Dovrebbero essere tutti uguali questi valori se sono tutti lo stesso metodo per calcolare. No? If all of us use the same regression method to find the slope,
You will not find the same number. You will find number, we hope, very close.
okay,
not
but we use the same method.
Yes.
So how we understand, this AR is theoretical.
This AR comes from a mathematical calculation, that is this.
I understood, but all of us use this mathematical calculation to find the AR.
Yes, but how can I say? When you let us go back to the simple example of measuring the volume of this bottle. The volume, the expected value is 1 liter. You all infinite operators apply the same procedure of weighting several times, and you obtain an average and standard deviation,
Yes.
but the reference value is written on the label. That is the value, the real value, the true value
Yes.
of this. The analogous of 1 liter is AR, that comes from a calculation. And each operator will find some experimental values that are close to that,
Okay.
but not identical. I know it is very abstract concept, but the general statement is this: when I apply any procedure, I obtain a distribution of values, not a single one. So I should accept the fact that all the possible values of the intercept are on a Gaussian distribution. Maybe I can answer your question.
No, yes, okay.
Is it clear for all? Because why all the operators could find the different values? Because
Maybe because they use different concentration.
because their manuality is different, for instance. No, the concentration are the same.
Okay.
Because the procedure is the same. But there are random errors. So the values of AI can change. So what we do? We take the results obtained by one operator, me, I am one operator. We take them, the results of one operator, me, and perform this calculation on my results. And this is AR. And when we obtain the intercept from the slope of regression, and I can predict that if infinite operators replicate my experiment, they will find a distribution whose maximum is what I have found, but they can be disturbed. It is what I mean. So, in the ideal hypothesis of replicated infinite time with infinite number of standards, I obtain a distribution. And Excel can calculate this distribution because Excel gives to me the value, the most probable value of the intercept, and also its standard deviation. Okay?
So could we, for example, say that AR is simply the maximum of this
Yes. AR is the maximum of distribution. That is, the calculation that Excel makes from my results give us the best evaluation of the most probable value of the intercept.
Okay, yes, of course.
It's better.
Yes.
The same situation is for the slope, because those infinite operators can obtain many values of the slope, and I obtain a distribution where the most probable value is calculated by Excel equations, and it is BR, and we add the standard deviation of the slope. So both the parameters that I am calculating to create the model are described by a Gaussian distribution. Okay? So we said that an absolute statistic error is always the product between the t student of the problem and the standard deviation of the parameter. So, if the t-student of the problem is written as t depending on alpha and number of measurements on the standards minus 2, that is the t tabulated for our problem, how can I write the delta intercept? How can I write delta slope?
AR plus minus.
Sorry, I am just calculating the R. Delta A.
Okay.
Only delta A, not the confidence interval. Only delta A.
T A that T times
Okay, T tab is the same
as A
times as A. And the absolute error on the slope is the t-student of this problem, regression, multiplied as B. Okay? Okay, let us write the confidence intervals. So, confidence interval for the intercept is AR plus minus T tab multiplied as A, and the confidence interval for the slope is BR plus minus T tab multiplied as B. Look that these standard deviations are not coming from an average. They are coming from regression. There is not divided by the square root of n, because they come from regression, not from an average. In other words, when you perform a direct measurement, x average is associated to S of x average. When you calculate the intercept, it is associated with the standard deviation of the intercept. I want to conclude just 5 minutes with this part, and then in the afternoon we go on with theory, because theory is still to be concluded. Okay?
I'm sorry, why there's no division for the square root of the values?
Because you have not measured directly the intercept and made an average. You have obtained the intercept from a regression method. In other words, I can say, for direct measurement, an average is associated with the standard deviation of the mean. And this is the standard deviation of the sample divided by square root of n. In a regression, the intercept is corresponding to SA, and that's all. SA comes from minimizing process, okay? And the slope is associated with a standard deviation coming from the calculation to minimize the standard deviation of the regression.
Here we can write R and DR, and DR.
Yes, but in general I indicate here A as the slope resulting from regression. Okay. If If you want, we can put the subscript, but in general we write intercept. So you see the analogy is this corresponds to this and this corresponds to this. In the first case, the standard deviation of the average is obtained by a certain calculation. In the second case, we obtain the standard deviations for the intercept and the slope by a regression procedure, not by an average. Just 5 minutes more, then we will take 1 hour break anyway. Now, look to this plot and tell me the value of AR should be close to 0 or far. Should be close. So I would like a situation like this, where the value 0 is closed, and this high area is high. Okay? This is the situation that I want. In this point, I have the value 0, and the maximum of the distribution is closed. That area is p-value, the p-value of t-test on the intercept. Let us write it. So, t-test on the intercept. Okay, I have to calculate a tk, that is a fraction, numerator an absolute value, denominator a standard deviation.
Sorry, Professor. The area of the p-value is just the one.
No, it is two tails. I plotted only one for simplicity, but of course we have two tails. This is the p-value.
Okay. And why we needed a decay for the p-value?
Why we need
the decay for the p-value?
Because you remember we can calculate the p-value by calculating a value of t corresponding to the reference value.
Yes, but here we don't have decay.
We can, how can I say? Okay, the problem here is to compare the value of the intercept obtained by regression with the null value.
Yes.
So I am evaluating the distance between the intercept and the null value.
Yes.
And when we performed a t-test, this distance was written as tk. Let us go to this. Because I said this writing is a general relationship. In the case of replicate measurement, the experimental is the average. The known is the reference value. And in the denominator, I have the standard deviation of the experimental value. When we are considering the distribution of the intercept, the experimental value is the value of intercept obtained by regression.
Yes, I know, but
the known, the reference is 0.
0, yes, but generally we plot the decay.
You can, in order to calculate the value in Excel,
I remember perfectly. But
we needed a t.
Yes, but generally we plot on the distribution the reference. Well, when we talk about the decay for the test, we plot the xk, and of course we introduce the t as a function of as the value of t that corresponds to xk. So in this case, tk corresponds to which value in the distribution?
Tk corresponds to the position of 0 with respect to A, to the intercept. Tk is measuring the distance between the intercept obtained by regression and the null value 0. I want that the intercept obtained by regression is very close to 0. I want that this distance is low, small. Okay? This distance is given by the difference between the intercept obtained by regression and the null value. And this distance should be divided by the standard deviation of the intercept. Let us try to conclude and think about the conclusion. I have performing a test on the intercept. I will explicit another comment to compare. I'm tired. I need food. To compare it with 0. This is what I am doing. Okay? No, okay. Let us try to write what I want to discuss. The t for the t-test is the absolute value of the distance between the intercept coming from my experiments, so A, R, minus the value with which I am comparing this with. And in the denominator, the standard deviation of the distribution describing the intercept. This is the t-test, the tk. Okay? And of course, it is equal to the intercept divided by its own standard deviation. This is the tk. And it corresponds to a p-value and to a t-tab. That is this same t-tab, this one. So I can conclude.
Yes.
Yes. Oh, sorry, sir. sorry. This is essay. Yes, sorry. Okay, so now I compare the TK. Let us explicit also the subscript. So this is TK for the intercept. Okay? And I want, from a subjective point of view, I want that TK for the intercept be lower than T tab. And so I conclude that A, the intercept, is not significantly different from 0. And it is equivalent to say that the p-value for the intercept be higher than the significance. This is the subjective conclusion. And the objective is that the intercept, the p-value of this intercept should be as close as possible to 1. Very high similarity between the intercept and the null value. Because the value is the similarity between the two compared values. So high p-value, high similarity between the intercept and 0. Could you guess what I desire for the slope? Because let's have a look at this. I want a high slope or a horizontal straight lines. Very high. Because if I have horizontal line, I cannot read nothing. So I want this model to have a very high slope. This means high sensitivity. Means that changing a little the concentration, the area will change a lot. So B, the slope is sensitivity. And I want the slope to be very, very high, very distant from 0. So what I desire is that in the case of the slope 0, be very far from the B obtained by regression. So I want a very low p-value, a very low similarity between the slope and 0. Concluding, and then we eat something, otherwise we cannot resist. So, t-test on the slope. T-test on the slope to compare it with the null value. So the TK for the slope will be the B obtained by regression minus the null value divided by the standard deviation of the slope Of course, it is equal to the B obtained by regression divided by SB. And we want TKB higher than T cab. That is, we want P value for the slope tending to 0. So we want very low similarity between the slope and the null value. Okay?
But why do we want the slope to be 0?
We want the slope to be very different from 0. So low similarity. Okay? So and so.
And so we want the value is lower than the significance
Yes.
also.
Yes. Okay, we can also write that, it is useful. We want the P value for the slope much lower than the significance. Okay, it is difficult because it is very theoretical, but I think that you have understood the basics. Now we take 1 hour for the lunch, so we start again and 30 minutes past 2 o'clock again. And we will study how to associate an error to this value. Sorry. Okay, we want to study how to associate an error to the interpolated concentration.
And sorry, Professor, we will say also how we choose the concentration.
Yes, the consequence of this study, the trend, there is a formula describing C0. And by analyzing this formula, we will conclude the best choice for C1, C2, Cn. Okay? I think I will take 1 hour lecture and 1 hour showing the exercise, and tomorrow you will have time to do the exercises.
And the other person,
Your questions?
I'm not sure to having understood the difference between calibration and creating the model.
And
creating the model. I mean, for me, calibration is creating the model.
Yes, performing calibration implies to create a statistical model.
Okay, but if you ask me what is calibration, I have to answer that it is the statistical method to obtain the equation that is the best estimation of the function.
Yes.
Okay.
Or in other words, calibration is the statistical procedure that allows us to create a model that is the best estimation of the true equation linking the response to the independent variable.
Okay. And the true equation is theoretical.
It is theoretical, and sometimes you can also not know it. You can only hypothesize, make the hypothesis that the function is linear.
Okay.
And then you create a model. But in this case, we know the theoretical equation, and it is easier to accept that the model is the green value, the green equation in this slide. Okay.